right. So thanks, everyone. So my name is Rodrigo Nogueira, and this is a joint work with my advisor from NYU, Kyung-Hyun Cho. And I will present our task-oriented query formulation with reinforcement learning. So let me begin by stating the dream that many of us might have. That is a machine that can answer any complex question that you have. For example, in this neural net days, we can simply collect a very large question-answer pairs data set and then train a very large neural net to answer whatever complex question that we might have, right? But the problem with that is that learning all this knowledge in the weights of the neural net might be too difficult. So what if instead we learn how to access this knowledge and then come up with some answer based on what external knowledge we might have? So some related work that tries to access this external knowledge, that is memory networks, neural Turing machines, and attention mechanism. But however, these methods, they don't not scale well with respect to this external memory. In all of them, you either have to score the memory items to either read or write in your internal memory. So, for example, if you want to answer a question from using Wikipedia as your source, you have to score 5 million documents, and that might not be feasible in, at test time, let's say. So what if we use a search engine to access this knowledge? So there is some related work, recent work published Chain et al. 2017. So they used Wikipedia as the source. So given a question, they use a document retriever to retrieve a Wikipedia article, and then use a document reader to point to an answer in this article. And our goal is pretty much similar. We call it a research assistant. So given a question, an agent searches the internet and produces an answer based on what it read. So, for example, one question that I have, why does the film industry spend most of its money on movies targeted teenagers? We give this question to a search module, we retrieve some documents, and then there will be an answer module that makes a summary of what it read, and that'll be cool. And this talk is about only the search module, how we can improve it. We can use a search engine out of the box, let's say Apache Lucene, just to give a complex query and try to retrieve some documents, but that might not work well. So there are a couple of problems with that. I will name 3. So let's say you want to query the DeepMind Go paper, the one from Nature, pretty cool. You just go to Google, and boom, the top retrieved document is there, and you are satisfied. But then let's suppose you don't have the exact notion how to query that, and you just heard on the news about that, and you query Google artificial intelligence paper, Asian board game, you don't know exactly, so and give it to Google. Google will not return the document that you want. You will not understand that well. So you still have to go to one of these web pages and find the link inside and then click on that. So this is known as the vocabulary mismatch problem, which is the terms used by the user queries are normally different from the ones used in the documents, in the web documents. There's also another problem. When you give these complex queries to a search engine, even if you retrieve a large number of documents, the correct ones might not be there. So we did some testing here. We used 3 data sets that we collected, and we have this question and correct document pairs, and we give it to our Apache Lucene out-of-the-box search engine, and we measured the recall when giving these queries. And even if we have a recall of 10,000 documents, that is, we retrieve 10,000 documents and measure if the correct one is there, it will be only 75% of the times in the best case. So these using a search engine out of the box clearly is not the solution. And there is another problem, is that in the future you might want to have a conversation with the computer, and this conversation might be long and imprecise. Let's say you want to book an airline ticket or you want your computer to write the paper for you. So if you simply give this entire conversation to this agent and then use off-the-shelf search engine, it might not work well as well. So we need something that will convert these conversations into some useful queries. So that comes to our query formulation approach. So the framework it's a classical framework that was tried, I don't know, 30 years ago. It's you give it this long and imprecise query to a search engine, you retrieve some documents, and then you get those documents and feed to a reformulator together with your original query. And then hopefully this reformulator will give you a better query that will return the documents that you are interested in. And how we can train this reformulator is the novelty of our approach. So we use reinforcement learning. We have question and document pairs, the correct ones, and depicted here as the ground truth ones. So we give the original query to the search engine, retrieve some feedback documents that will be used to reformulate the query, give it again, the reformulated query to the search engine, and then measure how well these retrieved documents score compared to the ground truth ones. And this will give us a reward that our model can adjust, can learn something. And our reformulator is a pretty simple neural network. It's take as input the original query, plus some candidate terms, which are the original query concatenated with the feedback documents. For the original query, just take the embeddings, pass through a CNN or RNN, and then max pool over the entire sequence to get a fixed length query vector. For the terms, we have some surrounding terms as well. We feed them to RNN or CNN to get a fixed length term vector. And then we input these two vectors, the query and the term one, to a feed-forward neural network. That will give us a probability of adding this or using this term in our reformulated query. If this probability is higher than 0.5, let's say, you just add it to our new query. And we also have a value network or baseline network that will compute the predicted reward if we use the terms that we have. And we train using simple vanilla reinforce. So the cost here is the real reward minus the baseline one predicted times the sum of log probabilities of all the selected terms. And then we can compute the gradient and backpropagate. And then we also have the loss for our value network, which is simply the Euclidean distance between the real reward and the predicted one. And we don't propagate the gradients for this value network due to avoid some training instabilities. And yeah, that was pretty much the reinforcement learning method. It turns out there is another one that is a supervised one that you can collect a data set of positive and negative terms that you can append to your original query. It works as follows. You have your original query, give it to the search engine, measure the recall, let's say, and then you have a candidate term, in this case, DeepMind, and you append it to the original query. If the recall increases, that term will be labeled as positive. If it decreases, it will be labeled as negative, and then you simply train a supervised classifier using the same architecture presented in the last slide to predict positive and negative terms. And with that, we can also derive an oracle. That is a classifier that correctly only predicts, only selects positive terms. That will be our supervised oracle. We can also have an oracle for the reinforcement learning approach. This one is, you take the test data set, you split it into some, like a small subset, like 2,000 sample, let's say. And you overfit this RL model in each one of these subsets. And it can do pretty easily to overfit because there are so few training samples. And then the oracle performance will be the average reward over all the subsets. And this is, of course, is just a rough estimation. There might be other reformulation strategies that our algorithm was not able to explore, but at least give a rough estimation how well our framework can do. And to evaluate this approach, we use 3 data sets. We had to collect them because there are no such large data set available of query and correct document pairs. The first one is for the task of passage retrieval. The second one is question answering, and the third one is citation recommendation. So the first data set, it's We just downloaded a data set from the track competition. It's called Track Car. It's from this year. The input is a Wikipedia title, and put together, concatenated with a section title. In this case, in this example, is Sea Turtle is the Wikipedia title, and diet is one of its sections. And the desired output is all the paragraphs that are under that section diet. And what we index in our search engines are all Wikipedia paragraphs. So we have to retrieve the correct paragraphs from all the Wikipedia paragraphs. And there is a Jeopardy data set. This one was released last year by us. It's you just give a Jeopardy question from the TV show, and the desired output is the Wikipedia article whose title is the answer to that question. So as you can see, they're pretty long and complex queries, so it's kind of tricky to answer. And the last data set is the Microsoft Academic data set. We use Microsoft API, Academic API, to crawl 500,000 papers and use the title of those papers as the input, the query, and the target are the references in that paper. So in the end, it's the task of citation recommendation. You have an idea of a paper and you have the title in your mind, you just put it there, and then hopefully the system will retrieve the papers that you should cite it within. And here's the summary in terms of numbers. As you can see, there are hundreds of thousands of query and correct document pairs, which makes them suitable for a deep learning approach. And some results. We measure recall 40 and test set. Original query is just the original query given to Lucene. Pseudo relevance feedback is the classical one, where we select terms based on the top TF-IDF terms of our feedback documents. Pseudo relevance feedback, word2vec, is just the terms with embeddings that match, that are closest to the embeddings of the original query. And there's the Google baseline, that one we only could measure on Jeopardy data set, and we restrict the search only to Wikipedia domain. And of course, the supervised and reinforced approach that I explained in the previous slides. As you can see, the reinforced, it's better than the other ones. But our measures from the Oracle, it tells us that there's still large room for improvement. So here's some breakdown in terms of the architecture. If you use an RNN to encode both query and candidate terms, it's slightly better than the CNN, but not that much. There is also a sequential based approach that will encode everything using an RNN. And then you have also a decoder that you select one term at a time and use a hidden state just to be aware of the previous terms that you selected. This was implemented by a recent paper from Google Zurich. And it turns out that this less model RNN-seq performs a little bit worse than the simple RNN, but it produces queries that are 3 times shorter than the other approach, which makes it a little bit more favorable for production implementation. And here's some qualitative results. On the y-axis, you can see the probability of selecting the term, and Q0 is the original query, top 10 terms with respect to the probability, and bottom 10 ones. As you can see, at least in our interpretation, it's the top 10 are more related to the original query. So the model has kind of learned something useful here. And this one is also, you give a query, but this model is trained on different data sets. So the model trained in different data sets selects different terms. That's why task-oriented in the title of the paper. So for example, in the Jeopardy, which is a question-answer task, you can see that it selects proper nouns as if it's trying to answer some question for the query. And MS Academic tries to select broad terms related to community college, which are hospital, library, art center, etc. So yeah, in summary, we propose an agent that learns to access knowledge, and we believe that it's the good way to go forward if we want a pretty intelligent machine that can answer questions for us. And but there is still enough room to improve. Like there is a huge gap between the Oracle and the proposed model. And 40% of training time is querying the search engine, despite this being all distributed. And we also need some are algorithms with better sample complexity. It takes 1 or 2 weeks to train this model, although it's fairly small. And for production implementation of this approach, Microsoft, Bing, Google, all they have these click-through data sets, which are query and selected document pairs from the users of historical data, so they can use that to train. But as a research community, is there any other way to collect data so we can use ourselves? So the code and the data sets are available in our GitHub page. There is a link there. And yeah, that's it. Thank you.
All right, thank you. We have quite a lot of time for questions. So.
Hi, thanks. Good talk. Can you compare this to just like as a re-ranking feature with a neural net? Like instead of doing query refinement, you basically just trained a similar model architecture, and just use that score to train a re-ranking score to take the top 100 or whatever that Lucene spits out and select on top of that?
You mean like selecting the top terms?
Well, basically just doing supervised training, like training a deep neural network to do information retrieval and then using the model score of that as an additional feature with the original Lucene model score that it gives.
I see. It's like using the neural net to do some further ranking of the documents, or still on the query part?
Basically, instead of doing query refinement, just using a similar neural network architecture, and just training a information retrieval system as a deep neural network as an information retrieval system, and using that in addition to the original ranking. Mm-hmm. Like, how would you contrast that to what you did?
So it's kind of orthogonal. If we trained a neural net to just ranking documents, you can always further before this pipeline reformulate your query. So whatever improvement that you make in this ranking function, you can also do with this reformulation approach. I don't know if that answers.
But do you think that conceptually this is that they would have high overlap in terms of do you think that this is largely learning a ranking system and then just, because it has to omit a word that's effectively just saying, okay, if I pick this word, then this document will be at top. But it's really just learning that this is the right document to select and picking some random words from that document. Yeah,
that is the interesting approach. Like, yeah, you can definitely. We didn't try that, but we can in parallel train the same architecture to rank documents and see how it performs. But yeah, we didn't do that. Yeah.
So I was wondering. In the reinforcement learning phase, I didn't really understand. So how do you get the candidate terms that you add on to the query? Is this based on gold data? Is this based on what the first query returns, or is this the full vocabulary that you said?
No, we query the search engine using the original query, and then retrieve some documents, and then the terms in those documents will be our candidate terms, concatenate with the original query. So we first do this first round of retrieval to get candidate terms.
Based on the documents returned that you want returned, or based on all of the documents returned?
All the documents that are returned, okay. Not the ground truth ones. Yeah.
Interesting. And have you investigated also removing words from the query rather than just adding on?
Oh, sorry?
Have you investigated removing words rather than adding only words to the query?
Oh, yeah, we tried with the approach that we can also remove words from the original query, and it seems that adding it's always the best case. Like it doesn't help that much if we try to remove, because the model simply learns quickly to start selecting all the words of the original query. So it seems that it contains a lot of information, those original terms.
I see. Yeah. Thank you.
Yeah, nice talk. Mel from Facebook. So I have one question regarding your experiments. So in your experiments, you will do several iterations of the query write or something. So how do you decide when to stop the iterations?
Mm-hmm. So we try with many iterations, but turns out just doing one iteration gives the same performance as doing many. So right now our model just do one reformulation step.
So after one iteration, your query always become longer, or sometimes always become shorter?
In most of the cases, longer. Yeah, it quickly learns to not drop any of the terms of the original query. So in most of the cases, it's just longer.
Oh, okay, I see. Thank you.
Just along the same lines, does it just add a single word, or does it add just a combination of words? Because a naive implementation would argue that you just want to add until, almost on a greedy sense, right, until you don't have any positive words to add.
Oh, sorry, where are you?
Right here.
Where? Okay. Can you repeat? Sorry.
Right. So if you're figuring out which words are additive to increasing the probability and which words are negative to increasing the probability, then in theory you'd want to just add as many words as you can until it's no longer positive. Mm-hmm. So, like in general, like how many words does it add on a given query?
So we set a limit to 300 words, which is pretty large. And in the end, the model will roughly select half of them in our experiments. And the sequential one that sequentially decides which next term will output roughly select only a third of these terms. So on average, the query becomes much longer now. And yeah, it contains still a lot of common terms that shouldn't be there. And we believe that that's something that we should definitely improve in the model.
Hi, thanks for the talk. I have a quick question about your results. I noticed that your system performs much better for the first task, but not the other two. Could you comment out about?
So yeah, we believe that the other two are much harder. Like finding, it's like the first one is more related to the way the search engine was designed for, which is simply passage retrieval. And the other two was more question answering and citation recommendation. So we are not trying to find only the similar documents, but the ones that we should cite. So it's not we believe that is a harder test. That's why the performance there is not so large compared to these last two tasks.
So I was just wondering, using the current framework, and is it possible to add more things to improve the other two tasks, or that is just, I think, more promising for the first task?
Yeah, so we think that there's some interesting ideas that we can, of course, always parallelize and train longer. There is also some powerful approach, like we can make a structured query using some Boolean operators like and or to make this query a little bit more powerful. So we can explicitly not negate some terms. So we can add that to the framework, and hopefully we'll improve as well.
Okay.
All right, let's thank the speaker again. So we're a little bit faster than we have to be, so we're going to wait a couple of minutes just to give people from the other rooms a chance to come in for the next talk.
Done in 3 minutes, right? 3 minutes.
All right, so we'll begin again. We're going to stick to the theme of reinforcement learning in this session. So we've had 2 papers now on sort of question reformulation and making things more complex in order to answer things. And now Xinjin Chang, together with Mirella Lapata, is going to present work on making things simpler, sentence simplification with deep reinforcement learning. Thank you.
Okay. Hello, everyone. I'm Xinxin Zhang from the University of Edinburgh. This is the joint work with my advisor, Mirella Lapata. So this work is about sentence simplification. So why do we need sentence simplification? There's a lot of documents available on the verb, but unfortunately, most of them are written in formal and complex English, and children or second language learners may not understand properly. So the task of sentence simplification aims to make text easier to read and understand so that children or second language learners can understand. Specifically, it's a task to rewrite a complex sentence into a simpler one. It may involve several kinds of rewriting operations, for example, word or phrase replacement or word phrase deletion. The blue sentence is the original complex sentence, and the red sentence is its simplification. In the first example, most Americans favor the Defense Department decision is simplified to most Americans support, where the word favor is replaced with support, which is more commonly used. And the phrase, the Defense Department decision is simplified to the decision. It's an example of phrase deletion, where the phrase Defense Department is deleted. Sometimes it also involves sentence splitting. In the second example, the clause, with whom he had 2 sons, is simplified to be they had 2 sons. It's a brand new sentence. Okay. A lot of research has been done in the area of sentence simplification. People have tried rule-based methods where they mainly use some linguistic resources, for example, WordNet, or simplification dictionaries to replace the complex words in the original sentence with these simpler alternatives. They may also have a strategy to make sure the resulting sentence will be fluent or grammatical. Actually, a more popular way of modeling the problem of sentence simplification is to use monolingual machine translation, where the complex sentence is viewed as the foreign language and the simplification is viewed as English. People have tried syntax-based machine translation models, for example, Zhu et al. 2010. People have also tried pattern-based machine translation models, for example, Uben et al. 2012. In recent years, neural machine translation has achieved amazing success, and it's quite natural to apply neural machine translation models or sequence-to-sequence learning models to this task. That's what we have tried in the beginning. We view the complex sentence as a sequence, and the simplification as another sequence. Sometimes it involves sentence splitting. You may get several simplified sentences, but it doesn't matter. Just concatenate these short sentences with full stops. It's still another sequence. So we use the sequence-to-sequence attention model, takes a complex sentence in, and get the simple sentence out, and that's it. Seems like this is a happy ending. Actually, it's not. There's one big problem with the sequence-to-sequence learning model. It tries to repeat the complex sentence. But why does this happen? Apart from the rewriting operation we have mentioned earlier, actually there's one important rewriting operation. It's called copy, which is too common that we barely noticed. According to our statistics, from 70% to 80% of the words in the simplified sentences are actually copied from the original complex sentence. Actually, the sequence-to-sequence model is quite smart. It figures out that if I try to copy the complex sentence, I can get 80% of the words correctly. This is a shortcut. And